All right, diving in today, and I'm excited about this one. We're going to be looking at something pretty fundamental, I think. I mean, if you've ever thought about where math comes from, like really, or how we know what we know in math, this is going to be right up your alley. We're talking about mathematical truth, axiom systems, those building blocks, and those tricky limits of what we can actually prove.
Yeah, and we're going to be using this awesome entry from the Stanford Encyclopedia of Philosophy. It's called Independence and Large Cardinals, and it gets into some really deep stuff.
Deep stuff indeed, and that's what we do here, right? Deep dives. And today, we are going to try and make sense of these concepts: independence, interpretability, and these things called large cardinals. We want to see how they kind of shake up, what we thought we knew about the very foundation of math. And honestly, as a philosopher, I think you'll find the implications here are, well, pretty huge. I mean, we're going right to the bedrock of math. Where does it all begin? How do we even justify it? That kind of thing.
That's a great place to start. So before we get into these kind of more exotic ideas, let's talk about the basic structure of math, like, the ground level. We build all this amazing complex math, but it all rests on these things called axioms. So what are axioms? How do we know they are true? Like, where does the justification come from?
Good questions. So think of an axiom system like the starting point for a particular kind of math, right? It's the set of basic rules we accept without needing to prove them. Like you got piano arithmetic, we call it PA for short, and that sets the stage for how we understand, just basic numbers, counting, and all that. And then there's ZFC, that's Zermelo-Fraenkel's set theory with the axiom of choice, and that one's like the foundation for set theory, which deals with, well, sets. And the thing about these axioms, we don't prove them within the system. They're just the starting assumptions.
Right. And so the big question is, why should we just accept them?
Yeah.
I mean, are they just like made up?
Well, there are actually historically two main ways philosophers have thought about justifying axioms. One idea is that they're like self-evident. Their truth is just like obvious right there in front of you. The other idea is that they capture the very essence of what we're studying, the subject matter itself.
Right, and that leads to some pretty optimistic views, right? I mean, if you believe that axioms are self-evident, then you might think, well, all mathematical truths should be, like, derivable from those starting points. And if they define the very essence of what we're studying, you might think, okay, all true statements within that system should logically follow from those axioms. Kind of a neat and tidy picture.
It is, but in 1931, Kurt Gödel came along and, well, he threw a bit of a wrench into the works with his incompleteness theorems. And his second incompleteness theorem, that one's a real head-scratcher. It says basically that if piano arithmetic, is consistent, meaning it doesn't contradict itself, well, it can't actually prove its own consistency. Whoa, wait, so if I'm following you, it's like we're saying we can't actually prove that our most basic system of arithmetic won't lead to some crazy contradiction, at least not using just the rules of that system.
Exactly. And this brings us to this very important concept, the idea of a statement being independent of an axiom system. So with piano arithmetic, the statement PA is consistent, we can shorten that to CON-PA, that statement is independent of PA itself. That means that PA can't prove it's true, but it also can't prove it's false.
Mind blown. I mean, that's a pretty foundational statement about arithmetic, right? And our axioms can't say anything about it. And wait, this applies to other systems too, right?
It does. Gödel's theorem is really powerful. It applies to a lot of different formal systems. So even our most basic truths might be beyond our reach to prove within a particular framework. It's a bit like trying to see your own blind spot. You need something outside yourself to even see it's there.
So this whole self-evident thing, or defining the essence of what we're studying, that's kind of out the window, huh?
Well, it certainly gets a lot more complicated. Gödel showed us that no matter what axioms we choose, there are always going to be some mathematical statements that are just undecidable in that system. So if we want to answer those questions, those undecidable ones, we need new axioms. But then how do we justify those new axioms? That's a huge philosophical problem, especially as those axioms get stronger and less obvious, less intuitive.
Right.
Like, where do you even begin to find justification?
Absolutely. So what did mathematicians and philosophers do? Like, how did they try to address this?
Well, one early idea, and it was Gödel himself who suggested it, was to go beyond just natural numbers and look at a hierarchy of types. That means including not just numbers, but also sets of numbers, sets of numbers, and so on. The idea was to make our framework more expressive, more powerful.
Okay, so it's like expanding the language of math to handle more complex ideas. I like that.
Exactly. And this led to new, stronger axiom systems. For example, you have second-order arithmetic, PA2, which can actually prove CAN-PA, the consistency of basic arithmetic that PA itself couldn't prove. And then PA3, third-order arithmetic, can prove the consistency of PA2, and so on. It's like each level up answers a question from the level below.
So we just keep going up and up, solving the problems as we go. That sounds almost too good to be true.
It does, but unfortunately, Gödel's second incompleteness theorem, that pesky thing, it applies at each level of this hierarchy too. So PA2 can't prove its own consistency, and neither can PA3, and so on. It's like a ladder that keeps extending upwards, but we can never quite reach the top. Now, we can look at this hierarchy of types from the perspective of set theory. There, we have this concept of the cumulative hierarchy of sets, and it's pretty vast. It starts with nothing, the empty set, and we build up from there. We take the power set, that's the set of all possible subsets of the sets we've already built, and we keep doing this, creating a universe of sets, which we usually call V.
Okay, walk me through that again. I'm trying to visualize it.
Sure. So you start with the empty set V, Aereo, then V is the power set of that, which just has the empty set in it again, and so on. And when you reach the first infinite stage, V, you've collected all the hereditarily finite sets. These are sets that are finite and all their members are finite and so on all the way down. This level V satisfies a version of ZFC without the axiom of infinity. We call it ZFC infinity.
Okay, so ZFC infinity is like ZFC, but without the part that says infinity exists.
Exactly. And it turns out that this ZFC infinity is, in a sense, equivalent to Peano arithmetic. They're what we call mutually interpretable. That means they can express the same mathematical truths.
Whoa, so they're like different languages that can say the same things about the mathematical world.
That's a good analogy. And then if we go to the next level, V plus here, that's like the realm of real numbers, analysis, that kind of thing. And that level corresponds to PA2, then V plus 0, that corresponds to PA3, and so on. So these initial infinite levels of the set theoretic hierarchy capture a huge chunk of standard mathematics.
So it does seem like climbing this hierarchy might be the answer. Like if we just keep going higher and higher, maybe we can eventually decide all those undecidable statements.
It's a nice thought, but the reality is a bit trickier. Because it turns out that as we go up this set theoretic hierarchy, as our expressive power grows, we find even more of these stubborn, undecidable statements. And these aren't just weird edge cases. They're important questions that mathematicians really care about. For example, at the second infinite level, V plus 0, you have PM, the statement that says all projective sets are Lebesgue measurable. That's a deep question in real analysis. And at the third level, V plus 0, we find the famous continuum hypothesis, CH.
And these weren't just like puzzles for mathematicians to play with. These were serious questions that they wrestled with for decades and they couldn't solve them. Because it turned out these statements were independent of the standard axioms of set theory, ZFC.
Right. And that brings us to the work of two giants in the field, Kurt Gödel and Paul Cohen. Gödel, back in the 1930s, developed this method of inner models. He defined this specific inner model called L, the constructible universe. It's like a smaller, more controlled version of the full universe V. And Gödel showed that L satisfies the axioms of ZFC, and it also satisfies the continuum hypothesis.
So he found a world, this L world, where CH was true.
Exactly, which meant you couldn't disprove CH using ZFC. Then, in the 1960s, Paul Cohen came along with this really powerful technique called forcing. It lets you build outer models. You start with a model of ZFC, and then, using forcing, you add new sets in a very careful way, creating a new model with different properties. Cohen used forcing to show that there are models of ZFC where CH is actually false.
So Gödel showed that CH could be true, and Cohen showed that it could be false?
That's crazy. It is, and it proves that CH is independent of ZFC. The axioms just aren't strong enough to say anything about it. And we've found similar independence results for other statements, too, like that PM statement we talked about. It really makes you wonder, what are the limits of our understanding here? What does it mean for something to be mathematically true if we can't even decide it?
It's almost like a fundamental uncertainty baked into math itself. So what do? Give up?
Not at all. It actually spurred this search for new axioms that might be strong enough to answer these independent questions. And that's where Gödel's idea of large cardinal axioms comes in. He proposed this back in 1946, and it was pretty radical at the time.
What are large cardinals, exactly?
They're axioms that assert the existence of these, huge levels in the set theoretic hierarchy. Think of it like this. We're going to talk about levels like VO, VU plus Euro, but large cardinals are way beyond that. They posit these vast, almost unimaginable infinities. It's like stretching our concept of infinity to its absolute limits.
Wow. I mean, even VO plus Euro is pretty hard to wrap my head around. What's the point of going even further to these large cardinals, what do they even do for us?
Well, that's where the interpretability hierarchy comes in. This concept lets us compare different axiom systems and see like which ones are stronger, which ones can express more, that kind of thing. Basically, a theory TO is interpretable in another theory PO if you can translate all the statements in TO into the language of T and still prove the same things.
So it's like seeing if one system can simulate another.
Yeah, that's a good way to think about it.
Yeah.
And the source gets pretty technical here. They make some assumptions to simplify things. They're talking about theories in the language of set theory, containing at least Z of C infinity, and they also have this property called ES soundness, which basically means they don't say anything obviously false.
Okay, I'm following, kinda. So under these assumptions, how do we actually tell if one theory is interpretable in another? Like, how do we measure that?
Well, it turns out that under those assumptions, we can check if every statement, those are specific kinds of arithmetical statements that are provable in T, are also provable in T. If that's the case, then T is interpretable in T.
Right. And this ties back to Gödel, right? The incompleteness stuff.
Absolutely. So if you have a consistent theory, if you add con T to it, the statement that says T is consistent, you get a stronger theory. But if you add con T, the statement that says T is inconsistent, well, that doesn't really change the strength.
Huh. So saying a theory is inconsistent doesn't really add anything.
Not in terms of interpretability strength. It's a bit weird, but that's how it works.
Okay. So back to independence. You mentioned before there are different ways a statement can be independent. Can you unpack that a bit more?
Sure. So if we have a statement that's independent of a theory T, there are three ways it can be independent in terms of interpretability. One is a single jump, where adding or its negation to the T only makes it stronger in one of those cases. Another is no jump, where adding either one doesn't change the strength at all. And then there's double jump, where adding either one makes the theory stronger, and those two stronger theories might not even be comparable to each other.
Okay, that last one sounds pretty wild. Are there even examples of that, like in real math?
Well, we have examples, like Connie AT is a classic example of single jump. And we have these things called or sentences. They're examples of no jump. And we even have some really technical metamathematical examples of double jump. But the thing is, those double jump examples are kind of artificial. They're made up just to show that it's possible.
So what about real math, the stuff mathematicians actually work with? Are there any natural examples of these different types of independence?
Absolutely. In set theory, we have great examples for the first two. PM, that statement about Lebesgue measurability, that's a single jump. And CH, the continuum hypothesis, that's a classic no jump with respect to the ZFC. But here's the crazy thing. There are no known natural examples of double jump.
That's pretty interesting. So it's like the way independence actually shows up in real math is, well, more well-behaved.
Yeah, that's one way to put it. And here's another interesting observation. When we look at those natural mathematical theories, the interpretability ordering is really nice and clean. We don't have these infinite descending chains of weaker and weaker theories, and we don't have theories that are incomparable. It seems like the interpretability order on natural theories might actually be a well-ordering, meaning there's always a least element and everything is comparable.
So for the math that mathematicians actually do, there seems to be this clear hierarchy of strength.
That's right. And ZFC infinity is at the bottom of this hierarchy. So then the question becomes, how do we move up this hierarchy in a natural way? We saw that adding consistency statements can make a theory stronger, but it's not very satisfying. It doesn't really get us to the really interesting stuff.
Which brings us back to large cardinals, right?
Exactly. Large cardinal axioms offer this very natural and incredibly powerful way to climb this interpretability hierarchy. They extend our notion of the set theoretic universe in these enormous ways.
Okay, so concrete examples. Give me some large cardinals.
All right. Well, even the axiom of infinity can be thought of as saying there's a standard model of a very weak set theory. You've got inaccessible cardinals. A strongly inaccessible cardinal is this cardinal that you can't build from smaller cardinals using the usual set operations. And if you assume there is such a cardinal, well, that means there's a level of the set theoretic hierarchy, via UE, that satisfies all of ZFC itself. It's like a mini universe of sets within the larger one.
So it's like we have this, like, a Russian doll situation going on here. Universes within universes.
Exactly. And then we can go further. There are malo cardinals, indescribable cardinals, ineffable cardinals. A lot of these smaller, large cardinals can be motivated by these things called reflection principles. They basically say that the universe V kind of reflects properties that hold in its smaller parts.
Okay, and those reflection principles, they justify these smaller, large cardinals.
To some extent, but there are limits to how large they can go. And then we get to the really big ones, the large cardinals. These are so powerful that they can't even exist in Gödel's constructible universe L. And one of the main ways we understand these large cardinals is through elementary embeddings. That's when you have this function J that maps the whole universe V into some other class M. And this function preserves all the logical structure.
Hold on, mapping the entire universe, that's a pretty big function.
It is. And if this function J actually moves at least one set, then the smallest ordinal it moves is called its critical point. And that critical point is usually a very large cardinal. For example, a measurable cardinal, which is one of the, kind of foundational large cardinals, it's the critical point of such an embedding.
Yeah.
And we know, thanks to Dana Scott, that measurable cardinals cannot exist in L. They're just too big.
So we're talking about infinities that are beyond even what Gödel imagined with L.
Right. And we can keep going. We can make these large cardinal axioms even stronger by demanding that the embedding J preserves even more of the structure of the universe. And this leads to all these incredibly powerful large cardinals. Strong cardinals, wooden cardinals, super strong cardinals, super compact cardinals, and huge cardinals. They each push the boundaries of infinity further and further.
You said there's this ultimate axiom, but it's inconsistent. What's that about?
Well, you can imagine trying to say that the target class M is just the universe V itself. That would be the strongest possible self-embedding, right? But Kudin showed that's inconsistent. There's a limit to how much you can embed the universe into itself without contradictions.
Okay, so there are limits, even when it comes to these crazy large infinities.
Right. But there's still a huge space to explore within those limits. And the really cool thing is that these large cardinal axioms aren't just random, they're organized by their strength. If you assume a large cardinal axiom, you can often prove the consistency of the theory with a smaller large cardinal axiom.
I see. So they give us this really clear way to move up the interpretability hierarchy. Start with ZFC infinity, then ZFC plus an inaccessible cardinal, and so on. We just keep adding stronger and stronger large cardinals.
Precisely. And what's really remarkable is that many natural mathematical statements, including some of those independent ones we talked about, can be paired up with a large cardinal axiom. So ZFC plus that statement is mutually interpretable with ZFC plus that large cardinal axiom.
Wow. So it's like these large cardinals provide a way to translate between different areas of math, like a Rosetta Stone for different mathematical languages.
That's a great way to put it. And to show this mutual interpretability, mathematicians use these techniques from inner and outer model theory, like Cohen's forcing that's used to build outer models where the statement is true, and then you can sometimes collapse a large cardinal in that model to make things work out. And on the other side, you might build an inner model that can witness the large cardinal.
So in many cases, the only way we know to compare these different theories is by going through large cardinals.
That's right. They act like this central measuring stick for the strength of different theories. They bridge the gap between areas of math that seem totally unrelated on the surface.
This is definitely making me rethink the whole nature of mathematical truth. Like, if these large cardinals are so central, how do we justify them? I mean, they're way beyond anything, intuitively obvious, right?
Exactly. As a philosopher, I think you'll find this really interesting. So there's this debate in the philosophy of math between pluralism, which is this idea that there might be lots of different valid ways to extend our axioms, each leading to its own mathematical universe.
Okay, so multiple universes of math, each with its own rules.
Right. And the other view is that maybe ZFC, our current system, is just too weak. Maybe we need these large cardinal axioms to get the full picture of mathematical truth.
Right, so either we embrace the multiverse or we go looking for the missing pieces. And this whole well-ordered thing, that seems like a good argument for large cardinals, right?
It does, but the source points out a potential problem. It might be the case that all natural mathematical theories are well-ordered under interpretability, even ones that contradict each other. So well-orderedness by itself might not be enough.
Okay, fair enough. But what makes large cardinals unique? Why should we focus on them?
Well, they're not just well-ordered. They also seem to capture this notion of pure mathematical strength in the most natural way. Like, they're the most straightforward way to just express stronger and stronger levels of infinity. And crucially, they have this unique role as these intermediaries connecting different parts of math.
So they're not just strong, they're also like the connectors, the bridges between different mathematical worlds.
Exactly. And so the big philosophical question is, does this intermediary role give us reason to accept large cardinal axioms? Or at least should it encourage us to seriously investigate them? That's an open question and a really fascinating one. So
Yeah.
today we've gone from Gödel's incompleteness theorems to independence, to the interpretability hierarchy, and finally to these amazing large cardinals. It's been a journey for sure.
And as a philosopher, I have to say this really gets to the heart of what math is. How do we know what we know? What are the limits of our knowledge? It's almost like these large cardinals are forcing us to ask not just what's true in math, but what it even means for something to be mathematically true. And honestly, I think this is just the beginning of the conversation. I mean, if large cardinals can connect all these seemingly different parts of math, does that mean there's some deeper unity to mathematical truth that we haven't grasped yet? Is it just an accident that they work so well as these intermediaries, or is there a deeper principle at play? Lots to think about.